Dear students, welcome to St. Joseph Study Center Smart Class Session 5. In continuation to current electricity, we will see Kirchhoff's rules. Ohm's law can be applied for simple circuits in which we can find potential difference, voltage and resistance. When it comes to a complex circuits, we can apply Kirchhoff's rules. There are two types of law available: Kirchhoff's current rule, Kirchhoff's voltage rule. Kirchhoff's first rule, the other name is current rule or junction rule. It states that the algebraic sum of the currents at any junction of a circuit is zero. This law is based on law of conservation of energy. We know that energy can neither be created nor be destroyed. It will be converted one form to another form. So here at the junction, charges, it cannot be created or it cannot lost. So whatever the charge entering the junction, that has to leave from the junction. Based on this concept only the law has been framed. In the circuit diagram, you can note that the current I1, I2 are approaching towards point A and the current I3, I4, I5 away from the point A. In this circuit, we can apply the current approaching towards junction can be taken as a positive. The current leaving from the junction can be taken as a negative. According to the diagram, we can easily write the equation that current I1, I2 are approaching, so we can take a plus sign, and I3, I4, I5 we have to take a minus sign. The equations now become the current at any junction is equal to 0, I1 plus I2 minus I3 minus I4 minus F equal to 0, or I1 plus I2 is equal to I3, I4, I5. So the law says that simply that in any junction we can take the current approaching will be equal to the current leaving the circuit. The Kirchhoff's second rule is otherwise called as voltage rule or loop rule. It states that in a closed circuit, the algebraic sum of the product of the current and resistance of each part of the circuit is equal to the total EMF included in the circuit. Here we have to make use of the product of the current and resistance to find the EMF. These rules also follow the law of conservation of energy for an isolated system. That is, the energy supplied by the EMF source is equal to the sum of the energy delivered to all resistors. This formula we can apply in a rule where we can find the EMF by multiplying the current and the resistance. The direction of current is very important here. So the product of the current and resistance is taken as a positive when the direction of the current is followed. Suppose if you take it in an opposite direction, then we have to take the negative sign here. The same thing we can apply for EMF concepts also. The EMF is considered as a positive when proceeding from the negative to the positive terminal of the cell. Suppose if we change the direction, then it is taken as a minus sign. Here the current direction is taken also very important when it's come to the loop case. We'll see an example how we can apply this Kirchhoff's second rule in a loop-like circuit. We'll see how we can apply the Kirchhoff's voltage rule in a loop-like structure. Here we have 5 resistors connected to one EMF cell. In that you can see the resistors R1, R2, R3 forming one loop, then R4, R5, R2 again forming a second loop. In that loop, where the current going from resistor R1 sent through R3 finally reaches the EMF cell. So here all the resistance, the current action is correctly followed. So we can take all the products of the current and resistance, each junction can be taken as a positive. So now write the equation I1 R1 for the first direction, that is EMF to A. Then from A to C we can write the product I2 R2. From C to again the EMF cell E, we can write I3 R3. So this summation is equal to the EMF of the cell. When come to the second loop, we don't have any EMF, but look at the direction also. The current going from A to B is correctly following from B to C, but not C to A. So compared to A to B and B to C, A to C is in the opposite direction. So we can write A to B, that is I4 R4 plus then the second resistor R5, I5 R5, then the third direction is opposite to that, so it is not following, we can put minus sign, is equal to 0. So like that, this Kirchhoff's loop law can be easily applied for loop-like structures. So these are the two ways you can apply current rule and voltage rule. Now we can make use of this to understand the Wheatstone bridge experiment. This experiment is very useful in determining the unknown resistance value, or we can also compare the resistance. Here we are going to make use of 4 resistance and galvanometer and one EMF cell. These are connected in the as shown in the circuit diagram. Here we have resistors like P, Q or S. Usually this P is a branch where we connect the unknown resistance to find its value. The remaining R, S, Q will be usually known to us. The specialty of galvanometer is it can show the magnitude of the current as well as the direction, unlike an ammeter. Ammeter shows only the magnitude of the current, but galvanometer shows both magnitude and direction. Now we will apply the Kirchhoff's loop rule and junction rule in the circuit diagram. In the junction B, the current through resistor is approaching and the current through galvanometer and resistor Q is leaving, I1 as a positive, the current leaving from the junction we have to take minus sign. So we can write I1 minus Ig minus I equal to 0. Now take the junction D. In this, the current flowing through R is approaching, and also the current coming from Ig also approaching, but the current through S is leaving the circuit. So both the currents will take plus sign and this will take a minus sign. Now come to this equation, I2 plus Ig minus I4 equal to 0. Now we can apply the Kirchhoff's voltage law by taking two loops of the circuit. The first loop we take A, B, D. In that loop, the current flowing to the resistor, that is I1 through P1 and through Ig following the directions, then except the current flowing to the R. So both the directions of the current we can take as a positive and this become negative. Now we apply the voltage loop law. Along this loop, the product of the current and resistance is I1 into P plus Ig into G, and the current direction which is not followed we can take minus I2R equal to 0. Now come to the square loop. Now we apply the voltage rule in this loop. We can write the product of the current through resistor I1P plus I3 into Q. These two we have to apply minus sign, so we can write minus I4S minus I2R equal to 0. Now by using 4 equations we can find the value of P by this way. When the points B and D are at the same potential, the bridge is said to be balanced. That is, in the PQRS, usually we take S as variable resistor. By adjusting this resistor, we have to bring 0 in the galvanometer. Both arms of the circuit is balanced. In that case, we can write the current I1 minus Ig minus I3 equal to 0. We can take Ig as 0, so I1 become I3. In the second equation, again we apply Ig equal to 0. We take I2 equal to I4. Now in the loop, the current Ig equal to 0, therefore we can take I1P is equal to I2R. Now on substituting all these above equations in the final loop rule, that is the fourth equation, we can replace the terms like this, that is I1P plus instead of I3 we can put again I1, so I1Q, minus instead of I4 we can put I2 by this minus I2 into R equal to 0. Now separate the term both sides. Here you can take I1 as a common, here you can take I2 as a common. Now divide throughout this equation by I1P equal to I2R. Now divide this equation, we will have P by Q by P is equal to S plus R by R. Rearrange the terms like this. Split the term, you can cancel PP here, will get 1 here, and here RR you can cancel, get 1 here. Then you can cancel 1 at the other side. Then you have Q by P is equal to S by R. Just rearrange the term, will get P by Q equal to R by S. This is a very famous called as Wheatstone bridge equation. By making use of this equation, you can find any unknown resistor by knowing the 3 values. So this is called as a bridge balance condition. Under this condition, usually galvanometer has to show 0. Suppose we know the values of 2 adjacent resistors, the other 2 can be compared. Suppose if we know the R and S, we can compare the other 2 resistors, or likewise also you can change. If you know the 3 resistance value Q or S, then you can find the value of P. Like that, we can use this very famous P by Q R by S Wheatstone bridge equation to find the value of unknown resistance, or we can compare the resistance. You can also apply this Kirchhoff's rules in another experiment called as meter bridge experiment. Meter bridge is another form of Wheatstone bridge. Very interesting experiment you can perform in physics lab. The setup is very simple. It consists of a uniform manganese wire AB of 1 meter length stretched along a meter scale, parallel to a meter scale, and attached to 2 copper strips A and B. Then another copper strip E is enclosed between the 2 plates in order to fill the gaps G1, G2, and at the 2 ends of the E and C is connected by a unknown resistor for which we have to find the value. The other end of the E and strip B is enclosed with the resistor of Q for which we know the value already. You can connect a jack E to the terminal E by using galvanometer and high resistance. Then again this end of this wire AB connected to a Lagrange cell and a key to complete the circuit. This position of the key is movable. You can move anywhere according to the deflection of G. Once you make the circuit on, once you touch the G at anywhere the wire, you can notice a deflection. So what we can do is we can slowly move on the slide jack key somewhere to find the null deflection. Once you see the null deflection, the resistors in this arm is balanced with the resistor in the other arm, that is the resistor P, and this length corresponding to this AG is considered to be a R, and the length corresponding to J to B is considered to be S. So PQ RS. This all four resistors can be put in this formula provided if you have a deflection of G is equal to 0. If we move the jacky accordingly to find null deflection, we can make use of this formula. In the numerator you can see that instead of R we are writing R dash Aj. That is, if you take R dash as the uniform resistance per unit length, to this length Aj we can write as R dash into Aj. Likewise the other length J to B can be written as R dash Jb. Since there is a ratio value, you can cancel each other. We'll have simply the length Aj is equal to L1 and the length Jb can be L2. Therefore the value which we want to calculate P is equal to Q into Ln by L2. This experiment is very easy to perform to find the unknown resistance value P. But in this experiment, this point AB usually soldered. So this soldered material sometimes can introduce small amount of resistance in the circuit, that is called end resistance. To eliminate this error, we can interchange the P and Q. In the first experiment, you can where we have the P, no, second we have to change as a Q and Q can be put as a P. Again perform take the average of both experiment value, that may give some amount of errorless measurement. You find the specific resistance of the material, prepare like a coil like structure, attach at the point P, for which also you can find the resistance value, or even also calculate the specific resistive value, provided if you know the dimensions values, that is the length in which you are making the coil and the radius of the thin wire. If you know both the parameter, you can also calculate the resistivity of the particular material, because we have a formula resistance equal to resistivity into length by area of cross section. So if you want a resistivity, we have to rewrite the term resistivity equal to resistance into A by L. P is unknown resistance. The above equation become resistivity of the value you can calculate by making of this equation, that is by knowing the dimensions, area of cross section, length. We can calculate the resistivity of the material by using this meter bridge setup. Now come to the potentiometer. Potentiometer is advanced to meter bridge setup. In meter bridge we have only 1 meter of wire, but here we have a 10 meter of wire connected this by zigzag manner. It starts at one end and uniformly we have 1 meter length along all the path at end at another terminal. So if we measure all the length, it will become 10 meter length. So potentiometer is used for accurate measurement of potential differences, current and resistors. As I said, it consists of a 10 meter length of manganese or constant iron wire stretched along parallel from this end to this end. Each length is about 1 meter. The ends and B are brought to the same side to make the circuit connection very simpler. We also have a meter scale to measure the length. Suppose in the circuit if you include 3 lines, wires can be 3 meters and the portion can be again measured from the scale. So you can easily measure the exact position by making use of cell by counting number of wires in the remaining portions. A jack is provided to slide anywhere on the wire and you can easily count the length of the wire including the circuit. We have a wire of C to D and in series we have a one battery and one key. This is called as primary circuit. In the secondary circuit portion we have the cell for which we have to find the EMF value and galvanometer, high resistance jacky. So we have two loops, namely primary loop and secondary loop. Now we can find the EMF of the given cell by using a setup. It's given here. Look at, we have a known value of battery and a cell for which you have to find the EMF value, and we have a potentiometer here and a rheostat. So all this can be connected to the circuit. When you make the circuit on, this jacky can be moved along the wire. If the potential difference across Cj is equal to the EMF of the cell, then we will find no deflection in the galvanometer. That means the current will become 0 at this particular point. So the current, this battery also supplied to the wire, and the EMF also apply potential difference. At particular point both will balance and will read a 0 current here. So this length only we have to measure. So the potential difference across Cj you can express in terms of IRL, because potential difference equal to the product of the current in the length. Since if you take R is the resistance per unit length, then the length CL you can express as R into the particular length. You can write the equation very simply that EMF which you want to calculate is a product of the current in the balancing length, IRL. Since current in the circuit we have known, because we are applying here, and R are constant, the only the variable is length. Depending upon the EMF of the cell, we will have a different balancing length. So we can simply write the EMF of the cell is proportional to the length. So if you connect any number of cells here, for which you can find the balancing length, from which you can easily calculate the EMF value by using this potentiometer setup. In a general you can write the EMF of the cell is directly proportional to the balancing length. So by using this setup you can calculate the EMF value of any cell very simply. Thank you.